All right, we talked about the physical mechanism behind a hydraulic jump. We also did dimensional analysis to get a generic relationship between different variables. So we realized that, well, the only possibility is if h2 over h1 is a function of so-called Froude number. So the outcome of our analysis was this, that h2 over h1 is a function of v1 over square root of gh1, which we call a Froude number, right? So what we're going to work on now is to use dimensional analysis, not dimensional analysis, control volume analysis to really get an explicit format or explicit form of an expression for h2 over h1. So here's how we're going to proceed. I'm going to draw the schematic of the problem here. This is our surface fixed, and then we have a stream that comes to the right, and then there's going to be a lot of turbulence here, and then eventually we're going to have another stream going downstream. All right, yeah, lots of turbulence and other stuff here. All right, so what I'm going to do, I'm going to draw a control volume here about the flow just a little bit up above the surface, and there you go. So this is my control volume, and I'm going to write down the moment of balance for the control volume. So here's the equation: d dt of integral of rho velocity d volume plus integral over control surface of rho v dot n hat dA is equal to sigma of F external. Okay, now atmospheric pressure, we can just neglect that, i.e. we can work with the so-called gauge pressure. If you don't like that, just include the atmospheric pressure and the result is going to be exactly the same. It's a steady problem, so really the momentum, the first term doesn't contribute much to the integral. There's not much change in the momentum of the flow. In fact, there might be a little bit because of the turbulence, but that's second order and can be neglected. So the integral of the second integral, this one, we know that the only contribution is from here and here, the outlet and inlet, because through the other surfaces, there's no mass come and go, right? There's no mass come and go from this surface. There's no mass come and go from here, right? So therefore, there is no momentum input to the system or exiting the system with the mass. That's the physical meaning of the second term. So let's see what we get here. So we have rho. Now, assuming that the velocity is pretty uniform, and velocity here is v1, and velocity here is v2, height here is h1, and height here is, it can be nicer, h2. Therefore, for the inlet here, we have rho v1 and v dot n. V is in the positive x direction, assuming this is our coordinate system, or let's call the y-axis the z-axis because we have gravity. So velocity is in the positive x direction, and n hat for this area is in negative. So v dot n has a negative v1 value, and integrating over a1, so that's going to be h1 times b, and b being the width of the channel or the stream, as I mean, it comes out of the screen or it comes out of the paper. All right, so this is one term, and then the second term is for the outlet, and that's going to be rho v2 dot n gives us a positive v2, and dA is h2 times b, so that's the net momentum flux in and out, and then this has to be equal to the sigma force. Now there's a pressure here in the upstream, all right, and then assuming that the atmospheric pressure is zero, where we're talking about the gauge pressure, we know that pressure here is hydrostatic, right? So pressure is zero on the surface and then keeps increasing as we go down. And the same story here, pressure is hydrostatic, right? With the same slope. So it starts from small and then it basically increases, right? Okay, so how much is the pressure? and we assume atmospheric pressure is 0, so there is no contribution on any other part. So let's focus on the left-hand side and see how much force we have acting on the control volume or fluid inside control volume. From the left, we know that the average pressure is 1/2, I can use a different color, 1/2 rho g h1, and then I have to multiply this to h1 times b to get the net force acting in the positive x direction. On the other side, we have a similar thing with the negative 1/2 rho g h2 times h2b. All right, and that's it. There's no more force. We neglected the viscosity on the bottom surface here because we just said it's a small domain and there's no force from anything else in our system in the x direction, and this is the moment of balance in the x direction. All right, as you can see, there's rho everywhere, so let's get rid of rho, and there's b everywhere, so let's get rid of b, and what we'll end up getting is negative v12 h1 plus v22 h2 is equal to 1/2 g times h12 minus h22. All right. Now, also obviously from conservation of mass, we have v1 h1b is equal to v2 h2b. It's a steady flow, so the mass flow rate in has to be equal to the mass flow rate out. So b goes away, so therefore we conclude that v1 h1 is equal to v2 h2, right? So I can calculate v2 as a function of v1 here, so that v2 has to be v1 times h1 over h2. And then if I substitute this v2 back into here, right, what I'm going to get is v2 to the power 2. I'm gonna be able to solve for v1. So let's see how we do that. So I have negative v1 to the power 2 h1 plus v1 h1 over h2. This is v2 to the power 2 times h2 is 1/2 g h12 minus h22. Okay, therefore v12 times h12 over h2, and I'm doing a little simplification here, minus h1. All right, that's going to be 1/2 g h12 plus minus h22. 22. All right, this is just the algebra basically. So v12 therefore is equal to well, I can do one more step here. I can write this v12 h1 times h1 minus h2 divided by h2 is equal to 1/2 g h1 minus h2 times h1 plus h2, and then h1 minus h2 cancels this h1 minus h2, and I get an expression for v1. So v12 is 1/2 g h2 over h1 times h1 plus h2. All right, so this is an expression for v12, and then v22 is simply v12 times, we got the relationship a little bit earlier here. So v22 is v12 h1 h2 to the power 2. So that is going to be 1/2 g h1 over h2 times h1 plus h2. So we got the expression for v12 and v22. And now we're going to solve for h1 over h2. So I'm going to basically continue from here, or h2 over h1. So let's see what I get. So I have V12 is equal to 1/2 G H2 plus H22 over H1. All right. And if I divide both sides, so let's see what I have here. I have H2, H2. I can divide both sides by H1. So what I get is 2V12 over, and there's a parenthesis here, GH1, right, is equal to H2 over H1 times 1 plus H2 over H1. And now let me call H2 over H1 an X. So basically this expression is, I'll continue here, is X2 plus X minus, and I'm going to call this just a constant C to simplify our expression, minus C is equal to 0. So this is a second order equation, easy to solve. So X1 and 2, there are two solutions, is -1 plus minus the delta, which is B2, 1, minus 4AC, so that's 4C divided by 2B, 2. Okay, so therefore, there are two solutions for H2 over H1. Let's substitute. That's going to be -1 plus minus square root of 1 plus 4C. But remember, what is C? C is 2V12 over GH. So that's going to be 2 times fruit number to the power 2. And this is GH1, right? So that's going to be 1 plus 8 fruit number to the power 2 divided by 2. All right, so we got the expression that we were looking for between H1 and H2, right? And their fruit number. First of all, we just confirmed that, yes, the solution to the problem is as dimensional analysis predicted. Remember, the dimensional analysis said H2 over H1 has to be a function of the fruit number. And there you go. The only thing we have on the right-hand side is the fruit number. Second is we have an explicit relationship for H2 plus H1. But let's see under what conditions we can get a realistic solution. Case 1. If fruit number is equal to 0, then let's see what we get. So we get, therefore, H2 over H1 has to be either -1 plus minus 1 over 2. So it's either 0, which is in contradiction with the conservation of mass because that requires the velocity to be infinity, or -1. But this is also not acceptable because H2 cannot be negative H1, right? So physically not acceptable, not acceptable. Case 2, when fruit number is greater than 0, greater than, let's say, 1, right? Let's work with the 1 number. So here we get H2 over H1 is equal to -1 plus minus a number that is, because fruit number is greater than 1, this number is greater than 3, right, divided by 2, right? So therefore, it's going to be either, the -1 is, of course, again, not acceptable, but the positive one is going to be something greater than 2 divided by 2. So therefore, that's going to give us some like a number that is greater than 1, right? So it's like a 1.2. So it basically says H2 is greater than H1. And then case 3 is when fruit number is less than 1. In this case, we get H2 over H1, -1 plus minus something that is less than 3 divided by 2. Again, we get a negative answer that is not acceptable and a positive answer that is less than 1. And again, this is not acceptable because, as we're going to see, this requires some energy being pumped into the system. But we don't have a mechanism to do that. At least we didn't introduce this in this problem. So this is the general format here, the expression with two stars, and then for different fruit numbers, we're going to get different results as we discussed.